have you ever stopped to think if that AI helping you write an email could, accidentally learn your secrets? It's a bit of a scary thought, right? Well, today we're diving headfirst into a really fascinating paper that explores this exact risk. How the AI models we use every single day can unintentionally memorize and then leak your private data.
We're going to tackle this like a detective story. First, we'll discover this hidden, secret memory that AIs have. Then, we'll see how researchers set this brilliant trap to test for it. After that, we'll figure out how to measure the damage, prove the threat is very, very real, and finally, look at how we can build a safer AI for the future.
All right, let's get right to the heart of this paper. The core idea is actually pretty simple, but honestly, it's also pretty unnerving. It turns out that the AI models we interact with all the time can accidentally develop a secret memory of the exact data they were trained on.
I mean, just imagine this for a second. You're typing an email, and your phone's predictive text suddenly suggests something incredibly private and specific, something it should have absolutely no way of knowing. This isn't science fiction. This is the very real problem that these researchers set out to investigate.
So, what kind of AI are we even talking about here? The paper focuses on something called a generative sequence model. Now that sounds super technical, but it's really just a fancy term for an AI that's gotten incredibly good at one specific thing: predicting what comes next. The best example is that autocomplete on your phone or in your email that feels like it's reading your mind. That's it.
And this is a truly shocking result from the paper that shows you just how powerful this memorization can be. The researchers trained their model on a huge data set, and buried deep inside all that data was just one single time that a fake social security number appeared. Think about that, one sentence among millions, and yet, when they prompted the model with just the first few digits, boom, it perfectly auto-completed the rest. It had memorized a secret it saw only once.
Okay, so we know the AI can memorize secrets, but that brings up a really big question. How in the world do you even test for that? You can't just ask the AI for every secret it might have seen. So the researchers had to get really clever. They designed a brilliant test. It's kind of like a sting operation for AI.
And they did this using what they call a canary. Now, if you know the old saying, canaries were used in coal mines to detect dangerous gases. Well, these digital canaries are the same idea. They're unique, totally random pieces of information, like a fake credit card number, that are intentionally planted in the training data, just to see if the AI picks it up and memorizes it. The method they came up with is this really elegant four-step process. First, they just define the canary. They basically create a random secret. Second, they augment the data, which is just a fancy way of saying they slip that specific secret into the massive mountain of information the AI is going to learn from. Third, they train the model, just like you normally would. And finally, the most important part, they measure. They test the AI to see if it now prefers the secret canary it saw, treating it as more familiar than any other random phrase.
But how do you actually measure something like preference or memorization in an AI? You can't just ask it. You need a number, right? A score. So the researchers figured out a way to go from this vague sense of risk to a concrete, actual privacy score.
The first key concept you got to understand is called perplexity. Just think of it as a surpriseometer for the AI. If the AI sees a sentence and has a low perplexity, it means it wasn't surprised at all. It was like, yep, I saw that coming, that's predictable. But if it has a high perplexity, the AI is basically saying, whoa, that's weird, I didn't expect that.
And that idea of surprise leads us directly to the paper's most important metric, the exposure score. This is the number that actually quantifies the privacy leak. It calculates how much less surprised the AI is to see the specific canary it was trained on compared to any other random fake secret it's never seen before. So a high exposure score? That means the AI isn't surprised by the secret at all, which is bad news. It means the secret is badly exposed.
Now check this out. This graph shows something absolutely crucial. You can have two AI models that are equally good at their job, equally accurate, but have wildly different privacy risks. See that rising blue line? That's training strategy A. As it sees the canary more, its exposure score just skyrockets. But strategy B, the orange line, is way more resistant. This proves that how you train an AI is just as important as how well it works.
This chart right here, it completely debunks a huge myth about AI. A lot of people think models only memorize stuff when they're overtrained, trained for way too long. But look at this. The blue line, our exposure score, shoots up right at the beginning of training. It's happening at the exact same time the red lines, that's the model's error rate, are dropping.
This means the model is memorizing secrets while it's doing its most useful learning, not just as some weird side effect.
So, up to this point, this might all seem a little theoretical, but the researchers, they took it one critical step further. They proved that this memorization isn't just a risk on paper. It can be actively exploited by an attacker to steal real secrets. This is where it gets real.
So how would a hacker do it? Well, they could try a brute force attack, just guessing every single possible combination. But for a credit card number, that would literally take thousands of years. It's not practical. Instead, the researchers developed a much smarter attack, basically a GPS for finding secrets. It works by asking the model to predict the secret one character at a time, and it just follows the path of the model's most confident guesses. It's millions of times faster, and it makes stealing secrets a real possibility.
And this graph connects the dots perfectly. On the bottom, you have that exposure score we talked about, how much the secret is memorized. And on the side, you have how many guesses it took the attack to steal it. The link is crystal clear. The higher the exposure, the fewer guesses it takes. A memorized secret is an easily stolen secret, period.
And right here, this is the smoking gun. To prove this wasn't just a game with fake canaries, the researchers trained a model on a real-world data set, publicly available emails from the Enron scandal. And that data had real personal information in it. The results speak for themselves. They successfully pulled out real credit card numbers and a social security number directly from the trained AI. This proves the threat isn't theoretical. It's a real danger for our most sensitive data.
So we've seen the problem, and we've seen the proof of just how dangerous it is. But thankfully, the story doesn't end there. The second half of the paper is all about the solution. How do we actually fight back and start building safer AI?
Well, first, the researchers tested what doesn't work. They tried a bunch of common techniques, things like dropout and weight decay. These are the standard tools engineers use to help an AI learn general patterns instead of just memorizing everything it sees. But it turns out, for this specific problem of memorizing rare secrets, the paper found that these methods were completely useless.
The real solution, and this is a huge contribution of their work, is a powerful idea called differential privacy. The best way to think about it is like adding a bit of carefully controlled static or noise into the AI's training process. It's just enough noise to drown out any one person's specific data, like your social security number, so the model can't lock onto it. But it's not so much noise that it stops the AI from learning all the broad, useful patterns from the data as a whole.
And the results are just dramatic. Look at this. A standard model fully memorizes the secret, giving it a high exposure score, making it totally extractable. But on the right, the model trained with differential privacy, the exposure score just plummets. The secret gets lost in the noise. And here's the best part. You get this massive boost in privacy with only a tiny drop in how well the model actually works. It's a huge win.
And all of this leaves us with a final, really crucial question. AI is being baked into everything, from our keyboards to our medical records, and it's learning from our most personal data. This research shows us both the hidden dangers and a clear path to a solution, and it forces us all to ask, how do we build a future where AI can learn from us without ever learning to betray us?